Yes, thanks everyone for coming again, wherever you happen to be in the world. So today we're going to go, after yesterday's introduction to essentially setting up what the problem is we're trying to solve, today we're going to dive into the implementation and we're going to look at some of the fundamental things that we're going to need to think about throughout the implementation. So, mentioning fundamentals, I always hammer on about fundamentals, and it just occurred to me, I have right behind me. This is my favorite book on Go, Lessons in the Fundamentals of Go, and it's just kind of my favorite book on kind of teaching anything. Partly because it's written by it's written in the style of a grumpy old man. This is not necessarily a good thing. I just find it an entertaining style, but also because it hammers home the idea that if you don't understand the fundamentals of something, you're never going to get past a certain level. So I've kind of taken that. I'm still not any good at Go, but at least I've taken that lesson that you have to understand the basics. So we're going to do the basics of term representation. We're going to think about what the terms are inside an Idris program. So what exactly we have to represent. And then we're going to see kind of the syntax, how the syntax is represented, crucially how we deal with naming, and then how we do some term manipulation given that. So we're going to finally get to some implementation details of the real Idris system. So a few of you, or quite a lot of you as far as I could tell, were working through the exercises, the warm-up exercises, and there's one in particular, the one where there's an isvar type. So this isvar type is the way we're representing variables inside Idris. You'll see that they're represented as a de Bruijn index, but also as a proof that de Bruijn index is valid. And once you get the idea of the basic manipulations on that, you'll be doing it almost kind of automatically. So if you work with size, that's great. You're already a little way into the details for today. So I'm going to do one little diversion before we start. I want to talk about the core. I'll put it in quotes. The core monad. The reason I put monad in quotes is that for performance reasons, and this is largely down to a weakness in Idris 1. So for performance reasons, it's not actually an implementation of the monad interface. It's kind of hand-coded, hand-specialized implementation of the monad interface, and it was just down to a weakness in the inlining in Idris 1. I don't think Idris 2 has the same weakness, but I haven't yet been brave enough to see if making it monad instance would change performance. So I'll get to that at some point. But anyway, just to say, it says don't expect various monad functions that have a monad constraint to work with it, because it doesn't satisfy them. However, it's the context in which a huge proportion of the work happens inside the Idris system. It has to be, and it's just as an advance warning, necessarily the system is very imperative. There's a lot of mutable state inside the system. I make no apology for that. Immutable state is often very useful. It's a thing that we use throughout the implementation of Idris just to be faster than it would otherwise be. So you know, if this is something that bothers you, sorry, it bothers me a bit as well. But I also quite like the performance I get out of it. So there's IO rest, for example, for representing important parts of the state that we just keep updating. Anyway, I'll show you a bit of the mechanics of how that works, just because it's necessary to building everything else. But I'm going to spend most of the time talking about the core language, so the underlying representation TT. So TT is a cut down QTT. So the main things that are missing are the quantities on the binders. So it doesn't really add any complexity to add the quantities on the binder. No fundamental complexity anyway. So as far as we're concerned here, it would just add noise. So we won't worry about those. Also, we don't have let binders. Again, that doesn't really add any complexity in terms of the term manipulations. It does give us some additional things that we need to think about later on. But it simplifies things to not have let. So we're going to look at terms, we're going to look at how function definitions look, and we're going to look at how the resulting case trees. So we define things as pattern matching definitions, but in order to execute the things in order to compile them, evaluate them, and to help out with things like termination checking, coverage checking. We translate things down to simple case trees. So everything, every case, every pattern match clause, every pattern matching group of pattern matching clauses is translated to case expressions that only look at, that can only inspect variables, and that can only deconstruct one level of pattern at a time. So that simplifies huge amount, writing an evaluator, writing a compiler, all of the other bits of the system. And yeah, so we'll look at the core language, and then we'll look at how that's represented as an Idris 2 program, and we'll see how we take advantage of the Idris type system to deal with some of the issues that you typically come across when writing a language. So we look at things like weakening, so that's adding a variable, contraction, so that's removing a variable assuming it's not being used, and substitution, so substituting an argument into the body of an expression, so replacing a variable with an expression and then removing that variable. So this is where we got to yesterday, just talking about Tinyldris. So we're doing all of this in the context of Tinyldris. So the code samples I've given you today, I've just pulled them out of Tinyldris, so it's kind of even tinier Idris. So we're just focusing on TT itself without worrying about how that fits into the rest of the system. But it's good to see how all of the things fit together. And actually, there's a good point to say. So if you remember at the end of yesterday's lecture, I did a demo of Tinyldris, and I was a bit puzzled that I was getting some strange behavior. It turns out that there was a bit in unification where I accidentally solved an expression, or solved a variable with its type rather than its term. So I guess the lesson here is that types only get you so far. There's nothing magical about having dependent types in your system. It's still completely possible to make a mistake. In other words, you still need tests. So I mean, I guess you all know that really, but it's just something to bear in mind. We only get a certain level of confidence in correctness system. The rest of it, we have to rely on testing things properly. Oh, someone echoed. I just heard myself echoing back at me. It was slightly alarming. Right, so yeah, I fixed that bug in Tinyldris, and it comes up in unification. So we'll talk about that day after tomorrow. Anyway, there's a few things that the important things that you'll need to find your way around. So core.core, that's the in quotes monad that carries all of the context that is relevant to the particular bit of the system we're working on. So that's global definitions, the current unification state in particular. In fact, that's pretty much what it always is. The current the current globally defined names, so your nats, your vects, all of that. And the unification state, which is the collection of unification problems that we are currently working on. So as we elaborate a definition, there will be constraints that need solving. As we get further down the definition, those constraints will get solved. So the unification state carries those. So that's all managed by core. Core.tt, I'll put more on this tomorrow. It's actually more on this today. So TT and case tree we're going to look at today. Context is the global definitions, so that's pattern matching definitions, data constructors, type constructors, and then normalize, that's evaluate. I'm just like this. I always spell normalize with an S, even though everyone else spells it with a Z. A Z, I should say. I shouldn't say. So this is as a kind of childish response to whenever I was learning a programming language and I had to type color without a U. And that bothered me, so this is kind of my revenge on people who made me do that. And core.unify, again, we'll look at that on Thursday. So these are the main parts of the core system that we're going to work through, and then we're going to work through TTIMP, which is the surface language. So the surface language we're working with in Tinyldris. So there's also TTIMP.TTIMP, which defining TT that we're going to look at today with a little bit of embellishment to make it a little easier to use. Now, I want to, before we go into the TT representation, I just want to show you what the core monad-ish is all about. So, so this is the tiniest core program. So it's sort of my sort of initial implementation of checking that the I/O works. So you'll see, firstly, that core allows us to do. I don't like this actually, but it's just the way it is. Core allows us to lift arbitrary I/O operations. I have always intended, but never got around to, always intended to have some kind of restrictions on this, to say, in practice, the only I/O operations I ever want to do inside core are reading and writing from the array that represents the context, and logging, and that's it. And I've always intended to be a little bit cleverer about restricting effects. The main reason I haven't is, well, two reasons. Firstly, it was about the initial performance of the system. So I wanted it to be this to be as fast as possible, and that meant getting not having any needless abstraction overheads. And I think at some point when the system gets strong enough, we ought to put those abstractions back in, because say needless abstraction overheads, they're not needless. They help you write program correctly, but they're needless in terms of the runtime overhead that you get. So yeah, something that would be nice for later would be to restrict that a little bit more. But for now, we can do arbitrary I/O inside core, provided that we put it under a core lift. So all the and core allows us to unlike I/O. So I/O in Idris doesn't have exceptions. The Idris runtime doesn't have exceptions at all. So if you want exceptions, you have to define your own context or monad that has exceptions. So inside Idris, there is and this is just a placeholder, but so there is the possibility of returning an error. Now in the real system, there's a huge load of possible errors. Even in Tinyldris, there's a few possible errors here. So a core program is something that does I/O, and it might have an error that we can recover from. So to run a core program, you'll basically never have to use core run, because it's just run at the beginning of the program. It will run your main program. If there's a problem, it'll print what went wrong. Otherwise, we're done. Now, so far, core is just I/O plus errors. But something that we use throughout, so I mentioned I/O refs. We might want to keep track of some state, and we do want to keep track of some state, and we want to do it with minimal overhead. So something we can do is, I'll just show exactly how this works, directly how this works. So we can, when we define an I/O ref, we tag them with a phantom type that says what the meaning of that reference is. So at least we get some kind of safety that we're only referring to the things in the global. Well, we're kind of restricting the bits of the global context that we can look at in each function. So I could say something like there is a counter. There is a counter that's an integer, and I'll have to give it a name. But what we'd so even better than that, something we'd like to do is rather than having to explicitly pass these counters around, it gets really annoying if you have to explicitly pass the references around to all of the functions. So excuse me. So we use a trick with auto implicit arguments. So auto implicit arguments are arguments that when you call the function, the system will look for something in the context that has the appropriate type for the auto implicit arguments. I'm going to get a glass of water while you're thinking about that. Excuse me. Right, hopefully that's better. So yeah, an auto-implicit argument is an argument where the system will look for something appropriate in the context to fill it in. So it's kind of like having a global variable, just a little bit nicer. So if you've there's a paper from, I can't remember when now. So I think it was in the 2000s. So it's a functional Perl by John Hughes, where he talks about how to do global variables in Haskell. And it's basically by doing it by having by using implicit arguments. So we're kind of using a similar trick here. So we say that this C, this counter, is an auto-implicit, and then when we call core prog, as long as one of them is available in the context, it will pass it through. And this counter label makes sure that it's passing is a way of making sure it's passing through the right one. So I could, in this program, I could say count is get counter. So count, this again uses an auto-implicit to get the right tag, and I could do something like I could, count the number of times I've entered my name, and then we can put the updated counter back. So what remains is going to complain now if I try type checking that, because it says, well, in the main program, it can't find one of these implicit counters. So I have to create one. I have to initialize one somehow. So I can say C is a new counter, it's called new ref, and I'll give it an initial value. And now when I call prog, it successfully loaded it because it has a counter available. So so I mentioned this just because this is something that is all over the system. So we have fragments of a global state. Mostly it's the global context. So pretty much everything happens relative to a global context. Sometimes we have a unification state, so we need to know what the constraints are. And sometimes I add a little bit more here and there. So it's just a way of saying I just want to use a fragment of the global state, so I know which functions are going to influence which bits of the global state. So you'll see that everywhere. You need to know what it means. So back to the term representation. So this is there's a question. I can't see the chat today, so you'll need to either read it out or
Hi, Edwin. So the question is that do these implicit things do they need to be at? I mean, do they have a positional restriction on where in the signature of the function they need to be, or is it that they can be anywhere in the
They can be anywhere. As long as they are in most respects ordinary arguments. The only thing that's not ordinary about them is how they are filled in. So I could have no, I'm just making a couple of things up here. You could put it in the middle like that if you like. If by convention I typically put them first, but you don't have to. Okay.
Thanks.
Someone's cleaning my windows. That's the thing that doesn't usually happen during a lecture. Right. So so we're going to look at term representation. So these are the terms that we have available to us in the core type theory. So I'll just work through them quickly. Each one is going to have a corresponding representation in the Idris system. So we have variables. So here they're just names. So X is referring to a variable name. That could be either a global reference, so a nat or a plus, or it could be a local variable. We have binders. I like to treat this is just a thing that I like to do just for convenience in large parts of the implementation. So I like to treat all of the binders together. So we have lambdas, we have function spaces, the pi binders, and because we need to think about pattern variables, we also names that show up in pattern matching definitions. We also have pattern variables and we have pattern types as kinds of binders. So we have function application, just a function applied to an argument. We have the type of types. So for simplicity, we're just going to say that the type of types is type. So we have type in type. In fact, the current implementation of Idris 2 also has type in type. At some point, I'm going to add cumulativity again, just like Idris 1 had. The main reason I haven't is that it's just not very interesting to implement. And it's quite difficult to trip over type in type by accident. You can do it deliberately. So you can't currently trust the proofs that you have in Idris 2 because they might exploit type in type. So I will get around to it. It's just not there yet. And it simplifies the presentation here. Also, we have erased terms. So that's again, that's something that becomes more useful once you have quantities, because you might have the erased version that's going to get passed to the compiler, but we have it available in the type theory just for completeness. Obviously, it's not a hard thing to add. So that's all we have as far as TT in Tinyldris goes. Full QTT has a little bit more, so it's got quantities on the binders, so each of these things would also be annotated with a quantity. It's got lead binders, so a lead binder would be annotated with a quantity, and also the value that it's reducing to. We've got as patterns as well, and that just adds complexity that's not really anything to do with the type system. It's just something you have to bear in mind. Also, we have explicit force and delay in the core language. So in Idris 1, we had magical functions for force and delay. But in Idris 2, I found that rather than having magical functions and having to check if it's the magical function somewhere, it would be a good idea to have those in the core language. So again, that doesn't really affect much about how we're implementing the core. It does affect how the system is compiled. So you treat force and delay specially. So we have definitions. Definitions consist of a type declaration and 0 or more pattern bindings. Typically, it would, if there's 0, it would typically be because you're defining something that's returning the empty type, so void. But so typically there'll be at least 1. So X is the function we're defining. T is the type of that function, so I'm just using T to stand for terms wherever. And then we have a series of left-hand side equals right-hand side. So notice I'm not doing any kind of checking here. This is purely about syntax. So when we're checking this, we certainly want to check that X is an application of the function X. We want to make sure that term, the parts of the term are, so it's only pattern matching on constructors, for example. So we're not going to check that here. We're just talking about syntax. We'd also, when we're checking, we also need to know that, for example, the left-hand side and the right-hand side have the same type. So additionally, we'll talk about these typing rules tomorrow. So just as an example, we've got these pat binders. This is I don't know if other systems do things this way. I've just found this a convenient way to do things. Because then we just always treat variable binding the same way wherever we happen to be in the system. So the pat binder just says I have a pattern variable. This is its type. And remember, this is just in the core language. This is not something. I mean, it is something you have to do in Tinyldris, but it's not something that you have accessible to you in full-scale Idris. So you've got we bind the variables, and then we have the left-hand side and the right-hand side. So whatever the variables are bound on the left-hand side, they are just also in scope on the right-hand side. So I haven't written these pat bindings again for the right-hand side. They would just be the same on the left-hand side. So they're abstracting over both sides. So this is what plus would look like. You've seen that in your little example of Tinyldris. So the other thing, or another thing we need to think about is what data declarations look like. So if anything, they're simpler than pattern matching definitions because they consist of a type constructor and then 0 or more data constructors. So a type can be trivially empty. So the type constructor I've marked by D here, and that has a type. So this T is this is if it's going to be correct, this is going to have to be a function type that returns a type. Well, not necessarily a function type, but it has to return type eventually. And each of these T1 to Tn, these have to return a D for it to be meaningful. So that's that's a bit of checking that we have to do. But really, all we're doing is introducing some constants. So T is a constant that stands for the type. C1 to Cn, they're constant names that stand for the data constructors. And the final thing we need is case trees. So this is, I guess, not strictly part of what the core language looks like, but it is the way, it's what we do to implement and evaluate expressions in the core language. So and I mean, we could do without them, but it's much easier to not do without them because we're gonna have to deal with them at some point anyway. So we have simple cases, case splits. So we can look at a variable x. We also this is partly to help with coverage checking. We also can calculate what the type of that variable is. So it's something we preserve throughout the representation of case trees. So we've got we do a case split, and then we have a list of alternatives. So these alternatives could either be is that a constructor, and is it a constructor applied to some variables? So if it matches that specific constructor, we will bind those variables, and then we'll carry on with more of the case tree. Or it could be the match anything case. So if you're matching on a variable, or if you have a catch-all case, so there's a match anything pattern as well. To get in full Idris, we need to think about primitives. We need to think about how to pattern match on ints and strings. There's not really any additional complexity there. It's just more stuff that you have to look at. So we've left it out here. And so eventually case trees will end up at a leaf. The most useful leaf is just if it's a term. So eventually we'll end up with a term. We'll have bound the variable case tree to some interesting values, and we carry on. We might encounter a missing case. So if you have something that isn't covering, you'll eventually end up at a missing case, or we might end up at an unreachable case. So in practice, the difference between these two things is how they come out of the coverage checker. So if the coverage checker gets to a leaf, or gets to a constructor that isn't covered, then it will insert a missing case. If it gets to a constructor that's not covered, but it's determined that one of the types on the way is an unmatchable type, then it'll insert this impossible. So that's the difference between the two is essentially how they're compiled. Now the coverage checker treats them. So just as a note on case trees, I basically, to implement this, the translation from pattern clauses to case trees, basically read off chapter 5 of this book by Simon Peyton Jones, The Implementation of Functional Programming Languages. So chapter 5 is written by Philip Wadler, and it explains how to efficiently compile pattern matching definitions to case trees. And this was written in, I think, about 1987, and the gist of it is unchanged. So obviously there's a lot more you can do. There's some optimizations you can do. There's a few more details that you need to think about for dealing with kind of force and delay, and dealing with primitives. But the essence of it is the same. So I'm not going to go into any more detail on that. It's just something that it's there for you to look at if you want to have a look at it. It's another thing that is pretty standard, essentially. Right. There are things we're going to be. Oh, there's a question.
Yes, so if you have case trees on the right-hand side, why do you have pattern matching on the left-hand side of definitions? Couldn't you make do with only binding variables in definitions?
You don't. You turn the pattern matching definitions into case trees. So we start with these, and then the definition becomes plus equals, or plus xy equals case x of. So we're translating pattern definitions into case definitions. So this is just the way we run them.
So the thing we saw earlier was not real TT syntax, the one where you had this path binder and this path y plus zy. So that's not real TT syntax.
So this is real TT syntax, but it's not something that we can easily evaluate. So we're going to turn these. In order to evaluate things, in order to do anything interesting, we need to turn these definitions into something that's more easy to evaluate. So that's where the case trees come in. So it's kind of like, if I've recognized your voice correctly, I think it was you who asked this on Slack about yesterday about translating to eliminators.
Yes.
I did. Good. it's kind of like taking one of these definitions and turning it into something a bit like eliminators, but without thinking about how to turn the recursive calls into the recursive part of the eliminator, the inductive part of the eliminator. So this is how we write them down. This is how we type check things. We always type check things to this form. Once we have something in a type checked form, we turn it into a case tree, because a case tree is something that's easier to run, easier to compile, easier to do almost anything interesting with. It's possible we could take it to the next step and turn it into eliminators. I'm not entirely sure how useful that would be in practice, but maybe it would be. Okay, so just before we go into the representation, we need to think about, thinking about how the representation is going to work, it's useful to think about the operations that we're going to need to do. So, because as you do the operations, you learn things about your representation that you think, well, maybe I should have dealt with that earlier. So let's set up the representation to make this easier. So what are the operations we're going to have to do? I picked this up from experience in Idris 1. So we need to deal with renaming variables. So we'll have a representation of names that helps us do that easily. So the problem with names is that people do have the tendency to use the same name for a lot of things, and that name is very often just X in a lot of cases. Yeah, we need to deal with the fact that people might use the same name in a lot of places, but we might also need to rename things for various reasons, just to check that two terms that might happen to have different names might have the same meaning. So we need to deal with naming. During type checking, at some point, we're going to need to compare some terms for equality. So we might have terms that terms aren't going to be equal if they're not in the same scope. So one part of unification, for example, is that we have two terms. Are these two terms the same? Modulo the meta variables, are they in the same scope? So the scope is something that we need to be thinking about. We sometimes need to substitute a term into the scope of a binder. So, for example, we don't actually do things this way, but let's say you're evaluating an application of a lambda. So you've got a lambda, you've got the argument. That argument is going to get substituted into the scope of the lambda, and then the variable that lambda binds is not going to be available anymore. So it's kind of we need to make sure that the result of that is well scoped. Sometimes we'll need to weaken a term. So, for example, we could be elaborating the scope of that lambda. So we kind of lambda x arrow some scope. So inside that scope, we might be referring to variables that are defined outside the scope, but it's still perfectly okay to use them. But they have an extra variable. So how do we make sure that we're referring to that variable correctly? Also, sometimes we might have a variable we're not using that we're just going to drop, so contracting the context. So that might happen if we're, again, during unification, this is the sort of thing that might happen, that you have an expression that uses a smaller context than the one that you, a bigger context than the one that you need, but it's not using all of the variables in that context, so we'll drop the ones that it's not using and see if it still works. So again, something we have to deal with, dropping unused variables. We have to think about variable representation when we do that too. And the lesson I learned the hard way from Idris 1, and everyone who has ever implemented a language will have learned this the hard way. I'm just asserting that everyone. I'm pretty confident that it's anyone who's ever implemented a language. That naming is hard. Things will go wrong. A huge number of the bugs I had to deal with in Idris 1 were about getting naming wrong. So the number one thing I wanted to do in Idris 2 was not have that problem. So you might get to a point where you think that you've got naming correctly, and then just something weird happens. So you're never quite confident that you've got all of the problems with naming resolved. So naming is hard. How are we going to deal with it? So to start with the representation. So now we've got the kind of core what we have to represent and the problems sorted. How do we represent them? So I said when I showed you the representation of TT, I like to think of binders just all together. I like to think of I like to combine them all together in the same way. I like to be able to write a map and a traverse over binders just because it's convenient. Just saves me writing code for all the binders separately. So we'll define a separate type for binders. We've got lambdas, pies, we've got pattern variables. Pattern variables themselves have to have types, so that's what pv_ty is all about. This pi info, this is something that we won't worry about too much. So it's something that we'll need to do after we've got unification working, is thinking about implicit syntax. So pi info really just says whether it's implicit or explicit. In Idris itself, it goes a bit further. We've also got auto implicits, we've got default implicits. But so it just says whether it's implicit or explicit here. And then the type, this is the type of the binder. So we're parameterized over the type of the binder. And that means whatever representation I choose for terms, I can use the same representation of binders. So it's convenient to be generic in the term representation. And we use it in at least 2 ways, I think exactly 2 ways in the implementation of Idris. So we've got it, we're using it for terms and we're using it for normal forms. We'll get to normal forms tomorrow. So we're just going to use every different representation of terms we look at, we're just going to use this same representation of binders. So a first attempt at representing terms, this is the kind of the initial simplest way you might think of, is we'll just represent names explicitly, and when we encounter a name, we'll worry about how to resolve conflicts between names then. So we've got variables, we've got binders. Binders will bind a name. There is a binder with a type, and then there is a scope, and then application is applying a term to a term, and then we've got the types of types. So we just need to add. We also need erased here. I've left erased out. So this is the simple way to do it, but it has, if you've tried implementing a language, or if you were at any of the lectures on representing names earlier in the summer school, you'll know that this is full of problems. So name clashes, certainly. Alpha conversion, so if you're comparing 2 terms for equality, you need to think, you need to keep track of the names of everything, and you need to keep track of any repeated names. You can't do things like, there might be things that when you're evaluating or substituting an expression, there might be, you might be using the same name to refer to multiple different binders, which is something that humans can't do very well, but machines can do internally. And you might have to defensively rename things just to avoid that kind of problem happening. Also, I find it really useful to have a distinction between local and global names. So it's useful to know during evaluation, during compilation, and all kinds of other places, whether a name you have is referring to a data constructor, a type constructor, a local variable, or a global function. And this doesn't give any hint as to what kind of name this is. So whenever you encounter this, you're going to have to do some work to figure out what kind of name it is. And most importantly, there's no help from the type system. So we don't do things this way, but it does at least give you an idea of what the term structure looks like. So the term structure we have, there's some relationship to this. We just have a little bit more information in there. So what Idris 1 did was something a bit more like this, was have a distinction between local names and global names. So local for local variables, and ref for things that exist in references in the global context. So we know which one. We know whether we're looking up a local variable or a global variable based on whether it's local or ref. So it's an improvement. There's still problems, which is that manipulating the Brown indices is hard. If you go back to, there's a talk from I think it's the Haskell Symposium 2009, where Bob Ackey is talking about domain-specific languages, and he says that ability to reason about the Brown indices is a Cylon detector. So you're clearly not human if you can just reason about the Brown indices yourself. So Idris 1 tries to do it that way, and that was the source of most of the naming issues, is just things where I should have been adding 1 or subtracting 1 and wasn't, so going under a binder and not dealing with things correctly. So there's still no help from the type system. Helps with things like comparing terms for equality, so alpha conversion is not a worry anymore, but there's still no help from the type system. So we could go a little bit further. We can make things well scoped just by the fact that they type check. So that's this is something I experimented with in early implementations of Idris 2, in fact, just to deal with this problem of getting the Brown indices wrong. So fin, if you haven't seen fin before, you could think of it as an integer bounded by n. So, so we're counting the number of variables that we have access to. So a local variable, there has to be something in scope, and this number refers to a position in the scope. So every term is annotated with the number of variables. So the interesting case is binders. If we bind a new name and the binder, so the type of the binder is only going to be able to refer to the things in the outer scope, but the body of the binder, or the scope of the binder, as I like to call it, is going to have one more name available. So we can add more variables by binding them, and the type makes that explicit. So this is a huge improvement because we no longer have the problem of accidentally making ill-scoped terms. So you don't get the thing that very occasionally happened in Idris 1 is it would just shout out you scope error, which is basically its way of saying I have confused myself and I don't know what to do. So you don't have that problem anymore because that would indicate a bug. So Idris 2 wouldn't compile if that kind of error showed up. Still problems though. I mean, there's certainly as a help from the type system. So weaken, suggested weaken earlier. This is where you have a term with n variables and you want to have an extra variable so that you can use it in a bigger scope. So weakening has a more helpful type. It doesn't have a perfectly helpful type because one of the difficulties with weakening is when you go under and you so if you're weakening something of the form bind, you go under the binder. You can't just add one to all of the variables because you might be adding one to the wrong variable. So the thing that you've added in the variables that are under the binder, you don't add one to them, but the variables outside that, you do add one to them. So you don't have that help from the type system, but you do have some help from the type system. So you'll get a well-scoped term. It just might be the wrong well-scoped term. So as an aside, you might think, well, can we go the whole way, and can we have terms indexed by their type? So this is an example you may have seen before because it's kind of the hello world of dependently typed programming. It's the well-typed interpreter. So we've got something representing types. So in this case, it's just natural numbers in a function type, and then our terms are indexed by the type. So any term that we can construct of this type is always going to be well-typed. So a variable. So I haven't said what has type is, but it's just saying that the ith thing in the context gamma has type t, and so the term has type t. And a value, if we can interpret the type a, then that term has type a. Lambdas, we'll add something. If we add something of type s to the context, then that gives us a function type s to t, and then application is take a function type s to t, an argument of type s, that gives us a value of result t. So you might think, well, could we go all the way and do this for TT? And I think, yes, we could. There's all kinds of complexities involved in doing it, but I don't actually think it's a good idea to do that. I think it's going a little bit too far, mostly because there's a lot of manipulations that we're going to need to do on terms in the later stages of the compilation process. So when we're working through erasure, for example, that we're going to lose a little bit of type information at some point, and somehow figuring out what we're going to do with these terms once we've thrown away that type information is going to get a bit tricky. But more importantly, it just makes things harder than necessary, in my opinion. And it's adding additional confidence in the correctness at the cost of making your programs significantly harder to write. So I think one of the things you're looking for in this type-driven approach to programming that I generally try to advocate, one of the things you're looking for is getting help from the type system, so making programs easier to write, making programmers more productive, but without also getting in their way. So it's really a question of how much safety, how much confidence you want in the correctness of the system. Like maybe one day we'll think, okay, now we're at a stage where we can do a verified Idris compiler. Let's go for it. But we're not there yet. So what I've gone for is something in between. So we're not just indexing terms by the number of things in scope, because I find that doesn't give quite enough information. It doesn't quite tell us what we need to do to implement, say, weaken correctly. Or, in fact, there's one example deep within the guts of the system, where we're shuffling variables around because we're working out the types of implicit arguments, and we're trying to work out which ones depend on the other, and sometimes we have to shuffle things in the scope to do that. So we've got a swap function that swaps the position of two variables in the scope. So if we're just looking at numbers, well, that's trivial to write. But it's also wrong. It's trivial to make it well typed, but it's just wrong. Whereas if we index terms by the names in the scope, not only do we know that we have the right number of things, but we have the ordering on things. So if we're introducing a new variable, we always have to introduce it in the right place. So we're going to use the Brown indices to represent variables, but they are going to be paired with a proof that so it's still going to be an index, a number, so we need a nat, but it's going to be paired with a proof that they refer to a name that's in scope. And we're going to use QTT, we're going to use the fact that we have quantities available to say this proof is not there at runtime. So this proof is purely to keep us right at compile time. The thing we have at runtime will be the de Bruijn index. So we get all the good things about the Brown indices, but without having, without tripping the Cylon detector by writing code that works without machine help. So this is the thing you might have seen if you did the exercises yesterday, mapping the Brown indices to a name and scope. This is how we represent variables. So a name has position position I. So name n has position I in context. I usually call this vars. So n's here. Oops. So the 0 thing in the context n cons n's is n, and if the nth thing, so the I thing is called n in context n's, then the I plus 1th thing is going to be called n in the bigger context. So this isvar is a proof that the name exists in the context. And then our representation of terms. So this is very close to the real Idris 2 implementation. So it is exactly the tiny Idris implementation. And the important thing, the difference between all of the others is how we're representing locals. So we still have the index, but we also have the proof that the index is valid, and we have the 0 annotation to say that the proof is not going to be there at runtime. We also have global references. It's got this additional annotation of name type. This is mostly there for it's useful to know just by looking whether something is a data constructor, a type constructor, or a function. It actually does make a difference to the performance of evaluation just by avoiding a lookup. It's a very small difference, but a difference nevertheless. We'll not worry about this too much today, but just to point out that it exists. We'll worry about this when we get to unification. But we have meta variables. Meta variables are some name that the system invents for your underscore applied to the current context. So a meta variable, when you solve the meta variable, you have the context in which that meta variable is defined available. So that's what this list of arguments is. We apply a meta variable to the context. And then the final interesting bit. So this is a bit like the bind we saw when we just had numbers, but instead of extending the scope with a successor symbol, we're extending the scope with a variable name. So by binding the variable name x with this binder in the scope, we also have x available in the scope. And then everything else, the application types, they just follow as before. Now then, I'm not going to look at case trees because we're running out of time. I just want to quickly look at some of the operations that you can do on this. So a nice thing about this representation is that you can, without, I was trying to cover up the screen with my hand, but that only stops me seeing it. You can look at the types of these things without looking at the names and pretty much work out to some approximation what they're going to do. So weaken is something that will add a new variable. Contract is something that will, given a term that has at least one variable, it will try to return a term that doesn't have that variable. So if this variable is used within the term, then it won't be able to do it, otherwise it will. So embed is something that we sometimes need to use if we're using an expression in a bigger context. So all global names, all globally defined names, they are terms with no local variables. So if we're applying a function, so the function name is a term with no local variables. If we're applying that to some argument in some context, then we're going to need to say, well, we're using this thing in a bigger context, so we can embed it in a bigger context. So this is adding the new variables at the end rather than at the beginning. Substitution, given some argument and some scope, it will, so this means that this will replace every occurrence of x with this argument in the scope. So it's kind of like contract, except when we encounter x, we replace it with this term rather than giving up. So rename is if we have two lists of variables that are compatible, which basically means they're the same length, then we can rename everything in one term with the other. So by the way, embed and rename at runtime, although we have to do some work to prove that these two things are correct, they're actually the identity function at runtime because of this representation that erases the proof. So currently Idris doesn't have a mechanism for noticing that things are the identity function, or even you being able to assert that they're at the identity function and have the machine check it. So if you look at the implementation, you'll see this suspicious looking call to believe me, but there is a commented out definition underneath that says, honestly, it's okay. This is what the definition looks like. Nice thing to do would be to have the machine do that rather than you have the assertion. Problem for another day. Right, just quickly, I've got some code of this representation in code that you can now work with. You can try implementing some things, but I wanted to show you a little bit of the implementation process, just because there are some tricks that you're going to encounter time and again when trying to write these. So the exercises for today are implement these things. Without any initial pointers, those implementations are going to be quite hard. So I'm just going to share with you some of the things that I learned the first time I tried to implement them. And I think the easiest one to do this with is probably contract. And I'm not going to do the whole thing, partly because we haven't got time, but also because I'll just show you the things that go wrong and how to get around them. So we'll do it the usual way of add an initial definition and then do a case split on it. So the names it's generated here aren't particularly good. We're going to focus on bind. Bind is the interesting one for what could possibly go wrong. So I'll rename these things just for convenience. And what are we trying to do? We're trying to return a term without this x. So we can start by recursively. I think this works. The version I've given you doesn't have traverse for binders, so you'll have to add that. But this version does. So we can recursively contract the binder. So we've got a contracted binder now. But we're going to run into trouble when we try to contract the scope. The problem with the scope is that contract only removes the first variable. And we've immediately seen where a place where having the names is keeping us right. If we try to contract the scope, we can't, because it's x we're trying to remove, and contracting the scope will remove n. So we'll get an x cons vars rather than the thing we need, which is an n cons vars. So we immediately see that we need to do something a bit cleverer. So the thing that's a bit clever, and again, this is a case of here's one I made earlier. Where's it gone? Up here. Oh, I didn't delete all of the definition either. The thing we need to do that's a bit cleverer is say, well, actually the thing that we're deleting, the thing that we're contracting is in the middle of the scope. So if you did that exercise with isvar yesterday where you have to look at outer, this is why I gave you that exercise. It comes up all the time in this kind of definition. So what we can do now, we'll do the same thing, case split. I'll just look at bind, and we can still traverse contract B, and we should be able to do scope prime is contract scope, but we need to tell it that the outer context is now, so it'll never figure this out for itself. The thing that we're contracting has one more variable. So as well as the things that we were already skipping, I should have done this in contract help. This is where if I'm doing this in a classroom, everyone shouts at me or everybody knows. But here I just have to find out for myself. Let's see if that works. Good. That's why I put this equals on the next line, by the way. I can do the alpha renaming. So that type check's okay. And what do we have available to us? We have our contracted binder. We have our successfully contracted scope. We're trying to make, that's our successfully contracted scope. We're trying to make something which is a term outer plus vars, and our scope just adds the x, so that's good. That's what we're trying to bind. So we should just be able to say bind x b prime scope prime, and we're done. Great. So most of these other cases are relatively simple. You just do a recursive contract on y and z. The final interesting case is how you deal with variables. So again, this is a case of, here's one I made earlier. So we're gonna need a way of contracting variables. So we're gonna contract this p. So this var is just a convenient wrapper for. We don't always want to put all of the things that are in the index for isvar. That's not always what we want to manipulate. That's partly what we're calculating. So this var is just a wrapper that doesn't have. It's a wrapper that has the interesting indices rather than all of the indices, or the currently interesting indices in this context. So the way to do that is to say, hope I've got this right. Let's contract make var of p. Does that work? Good, that type checks. So this p prime, this is a contracted version of p that that doesn't have the x. So it might have failed. That's why I'm doing this in the maybe monad. So we can now successfully return our local variable, and that should be it. So it's just the local variable p prime that I've just constructed. And again, in the interest of time, I'm not going to work through contract var, but I'm going to show it here so that you can see the general idea. So this is something that you'll have discovered for yourself if you implemented the drop var function yesterday, is that you have to look at what's in the outer scope to know which variable you need to drop. And then finally, if you get to a point where you're trying to drop something that you're trying to drop the thing that you're using, then you've lost. If you're trying to drop anything else, you're okay. I heard a ping, but I'm also going to stop there. So whoever pinged, do you have a question? Or can somebody read out the question if they don't have a mic?
Yeah, I'll read the question. Someone asked, wants outer to hang around at runtime, and several people
right, so outer does have to hang around at runtime, and it's something that you only really discover once you start putting these things in the type. So when I did this in Idris 1, I just kind of pattern matched on things without really thinking about it. But here you're thinking, hang on, I need to look at outer. And there's not really any way around it, at least not with the type the way it's currently defined. When you drop a variable, you need to know how much of the context you consume before you drop the variable. So that suggests that outer, or something like it, is a thing that you'll need to have hanging around. So there is one worry here. So one worry and one possibility. The one worry is that, I have to pass this list of names around every time I need to do this contraction. So two reasons why that's not really a huge worry. One is that in contract itself, so I'm just going to define contract as being contract helper outer equals nothing. So does that still type? Oh, because I called it contract help. Okay, so when we call contract, I don't need to pass the list in. So this x and vars, these are not around at runtime. So I've actually just created it here. It's when you're defining so we're defining a helper that's using this list as an index into how far along we need to drop something. So the only things that we're constructing here is some cons cells. So I guess we're we're not really constructing the name because we're getting it out of bind. So there's not an awful lot of things being constructed here. I mean, there are still things being constructed, which is something that is potentially costly. But mostly what's happening is where we're introducing a small number of variables as they needed as we go under a binder. And if you're worrying that that could be potentially expensive, then you're right to worry about that sort of thing. I worry about that sort of thing all the time. But I've profiled this on something of the scale of Idris 2, and they just don't show up in the profile. The length, the sizes of the things that we're looking at when we do these substitutions, because typically we're doing these on results of unification problems. Results of unification problems are either small already, or they are big because they involve results of other unification problems. So it's just a name. So the terms that we're doing this with in practice turn out to be really small. So in terms of performance and whether this is a performance problem, well, it is a potential performance problem, but practically it turns out not to be. So the opportunity or the possibility is just to think, well, is there actually a better way of representing terms? And maybe there is. So what you really want to do here, or the only thing you're really interested in, is the number of things that are in that outer list. So one possibility could be to index terms by a vector. So you have the length of A2. Another possibility, a little bit more fiddly, but could do the job, would be to say to have an additional argument here that is something that is parameterized by outer, or indexed by outer, where the runtime information that's available is a list. So something like I'm just going to. I don't know exactly how this would look, but no, that wouldn't be quite right, would it? I kind of want to have a nat that's going to be Z. Yeah, I don't know exactly what this would be, but I kind of want to have this nat being referring to something that's available at runtime, and then this list that's not. So I think by some kind of fiddly gymnastics, you could make it so that the thing you're looking at is a number rather than a list, but I just don't think you get any useful performance benefit out of it. And by the way, I really hope I'm wrong about that. I really hope that you would get any significant performance benefit out of it, because if you do, everyone's a winner. So so if you think there could be a performance benefit, please try it. I would be delighted to have just been completely wrong. I mean, it's always good to be wrong when being wrong leads to a benefit, isn't it? Anyway, I think I'm going to leave this on screen because the exercises for today are basically about writing this kind of definition. But the code I've given you doesn't have this helper material, so this is kind of up here now to give you some kind of hint in advance for how to do it. You can also look at the Tinyldris source to see how Tinyldris does it. It's a little bit more complicated in Tinyldris because for performance reasons, we don't always just drop one thing at a time, because every time we contract, we're traversing the term. So if we're contracting by more than one variable, we don't want to have to, and we know how many variables we're going to do. We don't want to traverse the term every time. So rather than just having the outer list, we have an environment that says which ones you're going to drop and which ones you're going to keep. I highly encourage you to look at how that works in Tinyldris, but try to implement it yourself in this simple way that just removes one variable, and then look to Tinyldris for hints if you get a bit stuck on that. And of course, I'll be around on the Slack as well, so happy to answer questions. If you didn't get the drop var from yesterday's exercises working, strongly encourage you to do that before you have a go at any of these substitutions or contractions, because you're going to have to do the same thing. But the hint in general, so for all of them, the top level type is not going to work in general, because as soon as you go under a binder, you've added another variable that's getting in your way. So you typically have to keep track of the outer scope as you do it. Right, I better stop there because I've overrun again. Sorry, folks. Yeah, tomorrow typing rules and evaluation. So we're gonna really get to how the thing works for writing real programs tomorrow. Right, thanks very much. Like yesterday, I'll hang around for a bit if anyone wants to chat. I'll probably hang around till about 4:30, and then I'll be around on and off on Slack in the evening, well, my evening.